Hello and welcome back to my Physics Online video lecture series. In today's video we're going to be talking a little bit more about the graphs that contain a loop with both an inductor and a resistor in them. I made a previous video in which I walked through the loop rules for such circuits as well as obtaining the equations for really for current, but for voltage as well. And so in today's video, I wanted to talk a little bit more about the graphs part of it. So we could kind of start by, doing our usual recall, or what was important from the previous video. And so you have essentially a circuit that looks like this, for example. In which you have an inductor and you have an EMF source, and somewhere along the lines there's also a resistor. And then essentially you turn on this circuit, so for example like close the switch. And so this one is sort of like the charging battery, the charging circuit, if you'd prefer to think of it in those terms. And what we ended up getting was that the current as a function of time should look like the maximum current, or sometimes I max, sometimes I naught, times 1 minus e to the negative t divided by tau, and so this is my charging circuit. And then similarly, we had the circuit in which maybe a similar setup to this one, where there is initially an inductor, a resistor, and then a battery, and then the switch is moved from closed like this to closed down here. So you have a closed loop without the battery. And in this case, the result was that the current as a function of time was equal to whatever the initial current is times e to the negative t over tau. And in both cases, tau is equal to the inductance divided by the resistance. So inductance, resistance, battery. Okay, so that was true for both of these cases. What do the graphs look like, and what can we get from them? All right, so I'm going to pull open my little bit of code that I've written, again in Octave, and I actually have already kind of plotted a figure for this. This is current versus time for the inductor and the resistor in the RL circuit. Specifically, if you look at what I've done in the code, I have two types of plots that can be made, and then I have two kind of things that can be plotted. So the plot type basically is telling me whether we want to have discharging or charging, and then the graph type is basically telling us whether we want to look at voltage or current. And so by choosing 1, 1, I've chosen the discharging and I've chosen current. Type can be either charging or discharging, and that's basically 1 is the charging type, and is the discharging type, and 2 is the charging type. Graph type means I'm either looking at voltage or looking at current. So that's a little explanation of what's going on here. So let's copy this graph over to our notes. And so this right here, this is current versus time for the inductor and the resistor in the RL circuit. Basically, I have a discharging, so this is discharging graph. So that would be like this one right here. We could call these like 1 or 0 and 1 if we're fitting the code. So 0 and 1. So this one right here is a 0. Okay. Now what can I get off of this graph? Well, quite a bit actually. First of all, I have this point right here, which is giving me my initial current. Specifically, it's where this curve is meeting with the y-axis. So I0 is 2 or maybe 2.0 amps. Second thing that I can get off of it, let's change colors for this point. We could say, therefore, half of I0 is 1 amp. All right, well, 1 amp is right here. And so that brings me to this point. And if I come down here, this right here would be my half-life, T 1/2 or half-life. So my discharging half-life is T 1/2. On a similar note, a quarter of I0 is 0.5 amps. And so this right here would be that quarter. I come over here, I come down here. This would be my quarter life, T 1/4. And etc. So the ratio we expect, given an equation that looks like this, should be that quarter life is twice the half-life. And sure enough, we see that quarter life is 2 milliseconds, half-life is 1 millisecond. That's the expected ratio. Half-life, for what it's worth, would be 0.25, and that ends up being roughly here 3, which is also as expected. An important point that comes out of all this is that my decay time constant tau is equal to the time that it takes to fall to, let's say, 1 over x, some fraction of the initial value, divided by the natural log of whatever the denominator of that fraction is, ln x. So, for example, if I can figure out the half-life, then to get to my decay time constant, I take that half-life and divide it by the natural log of 2. If I have a quarter life, then I take that quarter life and divide by the natural log of 4. And for what it's worth, due to the properties of natural logs, the natural log of 4 is twice the natural log of 2. So that's where that 2-to-1 expected ratio comes from. Okay. What about other possible graphs here? So let's pull back open our this thing, and let's plot graph type 0 instead of graph type 1. Sorry, I labeled this as type 1. It's actually a type 0 graph. Sorry, this was labeled type 0. It is a type 1 graph. So let's do a type 0 graph per our code. So let's run, which is this button, and let's pull open our plot. So here's the plot. Notice now that the plot is increasing rather than decreasing. But if you turn this graph upside down, you can see that it's actually still exponentially decaying. It's just that instead of decaying to 0, it's decaying from 0 up to 2. So that's how the charge basically works. So if we come back over here and we throw that graph in, this one really is a type 0 graph now. And again, this is the current versus time. So how do we get half-life, quarter-life, anything like that? Well, at half-life, we expect this to move from 0 to halfway to whatever it is that it's decaying to. Okay, so maybe we think it's decaying to 2. So that would mean that this right here is my half-life time. And this point right here, t 1/2 is, again, 1 millisecond. So to verify that, after 2 half-lives, or in other words 1/4 life, I expect to have reduced this distance between where I am now and where I'm going to by a factor of 2. So if I'm at 1 and 2 is the finale, I expect to be at 1.5. So now I look for where is 1.5 at. And the answer is it's right here. And sure enough, t 1/4 is equal to 2.0 milliseconds, which is 2 times t 1/2 as expected. So that means that I've been able to figure out from this my half-lives, my tau. Remember again that tau is equal to t 1/x divided by natural log of x. So it's actually the same equation for this as before. It also means that I can figure out my maximum current. So I max, based on this, is about 2 amps. And since I know my maximum current, I can figure out what my maximum voltage is. So note that we expect delta V max through, let's say, the resistor to look like I max times R. So as long as I know what the resistance value is, then I know what the delta V max is. So how do I go about getting the resistance value? Well, from just this graph and no further information, I cannot. But if I know one more piece of information, let's say the inductor's inductance value, then I can. So coming up here, as it turns out in the code, I give a value for the resistance rather than for the inductance. So how do you get the one from the other? Well, remember that tau is L over R. So if I know what the resistance is, then L will look like tau times R. And so what this basically means is my delta V max, noting that R is 12 ohms, my delta V max is 2 amps times 12 ohms. That means that my delta V max is 24 volts. And likewise, my inductance is tau, so let's say 1.0 milliseconds divided by natural log of 2. And that is this right here is my tau times R, which is 12. So plug it into the calculator, and we get L is approximately 17.3 millihenries. And that's basically it. From here, it's using stuff like ohmic power and the like. So thanks for watching.